Okay, ladies and gentlemen, this is my newly formatted June Physics Regents video where I'm going to go over every single question from last year's Physics Regents, June 2018 Physics Regents, all the way from question 1 all the way down to question 85. That's a lot, but again, I'm going to split up into 4 parts, starting with part A where I go over the first 35 multiple choice questions. Okay, and then part B1, we'll go over the next couple of set of multiple choice questions. B2, we'll go over the first set of free response questions, and then top it off with part C, the last 20 free response questions. So all of this entire 85 question exam will be broken down into 4 parts to be more digestible for you guys. All right, so let's begin. And we begin with our infamous first question that always asks about a scalar or a vector. And in this question, we're asked specifically about vectors. Which combination correctly pairs a vector quantity with its corresponding unit? So first, you need to identify which of these are vectors, and then on the other hand, you need to identify, is this the correct unit paired with it? Okay, so right off the bat, we could see that we have one scalar quantity here, and that's speed. Speed's a scalar. Now, down to the other 3 choices, each of these are definitely vector quantities, but 2 of them have the incorrect unit. And I'm going to cross off choice 1 for the fact that this here is supposed to be newtons. Weight is a force measured in newtons. If you're thinking about mass, that's kilograms. Velocity in meters per second, that actually checks out, so that's actually going to be our answer choice here. But I am also going to go down to acceleration and it's choice 4 and cross that off because this is also the incorrect unit. So instead of meters squared per second, it's supposed to be meters per second squared. That is the actual correct unit. I'm going to write some reasonings here as to why these are incorrect, just so you guys are aware. Okay, so our first answer choice is choice 1. Next, question 2, sorry. A 12 kilogram cart is moving at a speed of 0.25 meters per second. After the speed of the cart is tripled, the inertia of the cart will be, okay, so we're tripling the speed and we're seeing how inertia is affected. Well, we should know that inertia here is equivalent to mass only. Mass and mass alone. So it's going to be unchanged. That's why it's choice 1. If you're changing your speed, it has nothing to do with the mass, and so your inertia is unchanged. Number 3, while taking off from aircraft carrier, a jet starting from rest accelerates uniformly to a final speed of 40 meters per second on a runway that is 70 meters long. What is the magnitude of the acceleration of the jet? So we're going to start by underlining some keywords and values. So starts from rest, that indicates to you that initial velocity is 0 meters per second. To a final speed of 40 meters per second, so VF is 40 meters per second. And that the runway is 70 meters long, so distance is 70 meters. We are looking for the acceleration, where A is our question mark. So these are given values, and we need to figure out our equation. This is on your reference table in the back section, mechanics. And so I'm going to use this equation. VF squared equals VI squared plus 2AD. And that doesn't really show up well, so I'm going to use a darker version of it. Okay, let's use purple. So we're going to plug in just 40 squared equals 0 squared plus 2a 70. Pause in there so you could calculate. And you get that acceleration is equal to 11.42 meters per second squared if you calculate it right to the t, and you should get choice 4 as your answer. Okay, next, number 4. The 6 kilogram cart initially traveling at 4 meters per second east accelerates uniformly At 0.5 meters per second squared east for 3 seconds, what is the speed of the cart at the end of this 3-second interval? So now it's another type of kinematics question, and so we just have to again identify what we're given, figure out equation, and solve. So VI is 4 meters per second. That's a text message for me. I'll answer it later. Acceleration is 0.5 meters per second squared, and time is 3 seconds right there. What is the speed after at the end of this? So VF is our question mark. Once again, now look at your reference table. You could use this equation. There are 2 forms to it, so I'm going to use this form. VF equals VI plus AT. VF is what we're looking for, so I'm going to pause this here so I can plug. And you get your substitution and your answer here to be 5.5 meters per second, choice 2 as your answer for number 4. Okay, number 5, a soccer ball is kicked into the air from level ground with an initial speed of 20 meters per second, returns to ground level. Alright, at which angle above the horizontal should the ball be kicked in order for the ball to travel the greatest horizontal distance? That is also known as our range. Now there's 3 special angles when it comes to 2D projectiles. Well, we could already cross off each of these 3 because they're not part of our special angles. And it's 45 degrees, but let's just review some of these important angles. 0 degrees is the most horizontal, and that'll give you max horizontal speed. 45 degrees, we'll talk about that last, but 90 degrees gives you max vertical speed, vertical height, and air time. Now, why is 45 so special? Well, it maximizes both horizontal speed, which you need to go fast horizontally, but you also need some air time to actually travel in the air. Because if you go at 0 degrees, you're just going to plop right down. But 90 degrees, you go all the way vertically straight up and come back down. That gives you the most air time. It's directly related to height. So these 2 go hand in hand. The more height you get, the more air time. But at the same time, you also lose out on this guy. So 45 degrees is the nice happy medium between those 2 angles to give you the max horizontal distance. Because you want that nice, beautiful arc. Like that. To give you some air time and some horizontal speed. So that's why it's 45 degrees. So I'm going to write a special note, max range, dx, distance in the x direction. Okay, number 6, starting from rest, so I'm going to write vi is 0 already. Car travels 18 meters. The stylus is bugging. As it accelerates uniformly for 3 seconds. What is the magnitude of the car's acceleration? So now we're using the last of the big 3 equations. And that's v equals vit plus 1/2 at squared. I'm going to plug that in. And you get that acceleration is equal to 4 meters per second squared. That's choice 4. Okay, so for number 7, I thought I'd just save time and just already start with our drawing here of what is happening in question 7. And so you have a ball rolling off the table horizontally. So it has this certain trajectory path. We should remember that in 2D motion, horizontal motion stays constant. But in the y direction, it's affected by gravity. So there's always an acceleration due to gravity as it's falling through the air. And so we're looking for the magnitude of the ball's acceleration 0.2 seconds after it leaves the tabletop. Well, because it's always under the influence of gravity, its acceleration is always vertical, and there's nothing in the horizontal direction because it stays constant. Nothing's changing, no acceleration, no deceleration. Everything's in the vertical direction and it's affected by gravity, and there's only one number. There's only one acceleration due to gravity, and that's 9.81. Doesn't change, it's always 9.81 when you start and when you end. Choice 3. Okay. Number 8, a projectile with mass m is fired with initial horizontal velocity vx from height h above level ground. Which change would have resulted in a greater time of flight for the projectile? Okay, so kind of like what I talked about for a previous question, greater time of flight. Time and height go hand in hand. Oh my god, my stylus is acting up. Okay, so you don't have to talk about the mass. If you decrease the height, then you're losing out on some airtime. Whereas increasing the initial horizontal velocity, first of all, horizontal doesn't go with height, that's vertical. So it has to be choice 4. If you increase the height, more airtime. So more distance, more airtime. Vertical distance specifically. Okay, so a golf ball hits a stationary, oops, what happened to my stylus right there? Golf ball has that kind of a mass, average force of that many newtons, accelerating the ball to a speed of 44 meters per second. You know, people read that, they're like, oh, acceleration is 44 meters per second. But be careful. The speed is 44 meters per second, not your acceleration, just because you have the word there. So be careful of the wording. What is the magnitude of the impulse? Okay, so we're looking for impulse J with these certain variables. M is equal to 0.050 kilograms. Your force is 5 times 10 to the third newtons. Your VI is 0 meters per second. Your VF is 44 meters per second. Alright, so this is what they show you on the reference table. J impulse is equal to force times time equals to delta P change in momentum. So we got force here, but we don't got time. And we also don't got impulse. So I'm going to tell you, we're not going to use this part of the equation. Delta P, well, we don't exactly explicitly have a delta P, a change in momentum, but when you change a momentum, you are specifically changing the velocity, because P is equal to mv. When you change the momentum, you change the speed. And we do have a change of velocity and a mass, so we can use that equation. We'll use a different color. Alright, let's use green to darken it up a bit. Alright, sweet. Alright, so we got J equals the mass of 0.05 kilograms times your change in speed, 44 minus 0. Don't matter because we're just going straight to 44 from 0. Do that, plug and chug. And yeah, you get 2.2 Newton seconds. Alright, next, number 10. A tennis player's racket applies an average force of 200 newtons to a tennis ball for 0.025 seconds. The average force exerted on the racket by the tennis ball is, let's hold a second. Let's take a look at our objects here. 200 newtons from a racket to a tennis ball. So let's do this here. I'm going to put square boxes for our objects because who cares what shape they are. So we have racket and tennis ball. I swear my handwriting's prettier than this. It's my stylus that's bugging. Okay. Racket applies a force of 200 newtons. We are looking for the force on the racket by the tennis ball. So this one we don't know, but we should know by Newton's third law, our homeboy Newton. This law makes everything easier. Equal in magnitude. So that means these forces are going to be the same exact magnitude, same value, but opposite in direction. And that's what our question's asking about. So it's going to be 200 newtons in the other direction. You don't have to do any calculating. It's just 200 newtons. The beauty of that. You just got to be careful of the wording in your objects. So a racket by the tennis ball. Exactly. Wait, on the racket by the tennis ball. There you go. Alright, for 11 and 12, we got some big diagrams. Alright, so we start with number 11. Here we got an inclined plane. Those tend to be ugly problems, but this one's not so bad. So here the diagram below represents a box sliding down an incline at constant speed. Which arrow represents the direction of the frictional force? So the direction of friction acting on the box. Well, friction always opposes motion. So where are we going? We are going down this way. The V indicates its direction of motion. It's in the direction of B. But friction acts opposite to that, so it's got to be D. Alright, number 12. Which diagram represents the directions of the velocity v and acceleration a of a toy car as it moves in a clockwise horizontal circular path at a constant speed? Oh, I always tell you guys to remember these directions for circular motion. Okay, so acceleration is centripetal. And for those of you lucky kids to take Latin, or maybe not so lucky, centripetal has the root in their center, which means centripetal means towards the center. So we're looking for an A vector that points towards the center. Let's cross off 3, cross off 2. And we can also cross off 4 because it's pointing away from the center. But centripetal is towards the center. That's choice 1. And don't forget that v velocity is tangential. So tangent meaning it touches the circle at a single point, kind of scrapes aside like it's showing in choice 1. Charged particles located in an electric field where the strength of the electric field is 2000 newtons per coulomb. If the magnitude of the electrostatic force exerted on the particle is 3 times 10 to the negative third newtons, what is the charge of the particle? So we got an E electric field of 2 times 10 to the third, that's 2000 newtons per coulomb. And the force is 3 times 10 to the negative third newtons. We're looking for Q, charge, so there's only one equation. Okay, so you just plug it in and solve. And you get that Q is equal to 1.5 times 10 to the negative 6, or 1.5 microcoulombs, choice 2. Alright, 14. The magnitude of the gravitational field strength near the Earth's surface is represented by what? Alright, so this was a trick question that a lot of students, at least my students, got wrong. So gravitational field strength, if you don't know, it's also described in the reference table as lowercase g. And here I popped up their reference table. Here's a little snippet of it, because there's something here I want you to look at. So G here is our acceleration due to gravity or gravitational field strength, as I mentioned before. Now G here, well, don't we always treat that as 9.81? Yes, that is. It's our acceleration due to gravity at the Earth's surface, or near it. And there's an equation for that right over here. G equals Fg over m, or known as our weight equation, what we use to calculate for weight. And so that will lead us into choice 1, Fg over m. So G, gravitational field strength, is the same as the acceleration due to gravity, which is Fg over m, or weight over mass. There you go. And now I switched out of my headphones because I looked back into the audio and there's some weird screeching noise in the background. I apologize for that. So I hope now me speaking to my device, no headphones, would actually work this time. No weird screeching noise. I apologize. Number 15. A car engine supplies 2000 joules of energy during the 10 seconds it takes to accelerate the car along a horizontal surface. So yeah, 2000 joules. 10-second interval. What is the average power developed by the car engine while it is accelerating? So joules is work, supplies that many joules of energy, 2000 joules. With a time interval of 10 seconds, power is our question mark. There's a lot of straightforward plug and chug equation type questions here. I forgot how that one was like. Okay. So we got 2000 joules divided by 10 seconds because that's our equation for power. And power is 2000 divided by 10, and that's just 200 watts. Choice, ooh, now the trick here is scientific notation, and that's choice 2 is our answer. Number 16, which forces can either be attractive or repulsive? So this means there are things we have to remember, like repel, opposites attract. That's usually our sort of phrase to remember, that some forces with like poles repel and opposite poles attract. Gravity is only attractive. So we can cross off 1, 2, and 4. Wow, they made that easy for us. And so that leaves us with choice 3, magnetic and electrostatic. Opposites attract, likes repel. So that means there's both an attractive and a repulsive nature to those kinds of forces. Okay. All right, now the important thing about number 17 is that you need to read carefully for this question, because I was about to answer this question and leading you down the wrong path. But anyway, here we are comparing the resistivities of different length wires. So resistivity here, that's rho. Here we got different length wires, 0.4 and 0.8 lengths. The same diameter with copper wire between them both, and 0 degrees Celsius. So we should know that resistivity is rho, and that is not the same as resistance R. So while yes, all of these are factors of resistance, but resistivity is its own factor related to material. So because it's the same copper material, the resistivity does not change. It's only determined by the temperature and the material. Same copper material, same resistivity rho. And so it will be the same. I need to look at the percentage to see how many of my kids last year got that wrong, because I feel like that's just a reading question. All right, number 18. The work per unit charge required to move a charge between 2 points in an electric circuit defines electric blank. Okay, so here we are looking work per unit charge. So W over Q. And there is an equation for that. W over Q is equal to V, and that is voltage or potential difference. So this here is voltage or potential difference. And if we look at our choices, there's only one answer choice that fits it, and it's choice 4. So they're throwing some conceptual questions here at us that just require some reading. All right, number 19, here we got another electricity question with more copper wires. All right, so let's see. Here we got 2 meter length copper wire connected to a potential difference of 24 millivolts. The current through the wire is 0.4 amps. Same copper wire, same temperature, now through a different voltage. And now we're gonna see how the current is changed when you double the voltage. So here we're looking at our Ohm's law equation, V equals IR. So we are looking at the relationship specifically between voltage and current. R is constant because we're not changing anything about our copper wire. So now it's just V and I. So if V increases, so does I, and they increase linearly directly together. So if V is doubled, so will the current. So if our current is originally 0.4 amps, double that, you get 0.8 amps. Because our voltage goes from 24 to 48 millivolts, that's doubled. Double the voltage, double the current. Same thing if you think about voltage like batteries. If you put twice the amount of batteries, then you get twice the amount of current. That's easy to see for you guys. All right, number 20.
What is the magnitude of the gravitational force of attraction between two soccer balls when the distance between their centers is 0.5 meters? And if you look at all of our answer choices, these are very small, negligible newtons of force. That's why we do not see soccer balls sticking to each other when they're half a meter close to each other. Anyway, gravity is weak. So let's identify our variables. Let me use a different color. Let's use red. We got our two masses. We got our distance. We're looking for big FG. We got our masses. They're the same. And our separation distance is 0.5 meters. This means we're using this equation, the universal gravitation equation. I'm going to pause to plug it in, substitute, and then get the answer. And we get our answer to be choice 2, 4.82 times 10 to the negative 11 newtons. Now, if you look at my setup, I squared the masses because there are two identical masses being multiplied by each other, so you can square it. And then do not forget that r is squared in the bottom. That's a common calculation mistake. Because you forgot that, then you'll end up with choice 1. Okay? So don't forget some of these squares. A sound wave produced by a loudspeaker can travel through water but not through a vacuum. In comparison, a red light wave produced by a laser can travel through blank. Alright, so this now we're treading into wave territory, and we need to know the two types of waves. There's mechanical, and there's E&M waves. So mechanical travels needs a medium. They need material, they need matter to travel through. Whereas EM waves does not require it. And therefore, they can travel through vacuum. So examples of this, each of these, sound for mechanical and light for EM waves. So sound cannot travel through vacuum, but red light can. So red light laser can travel through both water and a vacuum, can travel through anything. Sound waves are mechanical, they can only travel through water, air, only matter, not vacuum. All right, number 22, a group of soldiers marches along a road. Each soldier steps simultaneously. When crossing the bridge, the group does not step simultaneously in order to prevent the bridge from vibrating intensely. The phenomenon responsible for the intense vibrations is resonance. Essentially, what this phenomena is, it's all wave related. The rest of these are not wave related, since we're in the subject of waves anyway. Resonance is essentially two objects vibrating together at the same frequency. So I'm just going to repeat that verbally. Two objects vibrating together at the same frequency. That's resonance. So the sort of group of soldiers marching simultaneously, they march at a certain frequency, just as the bridge is now shaking and vibrating intensely at the same frequency. So these two things cause resonance, and it causes a huge, huge transfer of energy, causing these huge vibrations. And that's resonance. It's beautiful. Okay, so now we're talking about refraction. This is with light. So when light travels from air to corn oil, there's a change of different medium. And when you change different medium, you also change the direction of light. As you can see, there's sort of an angle bend in our light rays going from air to corn oil. But if you also notice, the wavelength changes. So it goes from a longer wavelength to a shorter wavelength. So we could say that we can cross off choice 2 and choice 4 because wavelength definitely changes. Now, what remains constant? Speed, frequency, or period and frequency? In actuality, frequency defines the type of wave we have. Frequency keeps the identity. So frequency stays constant. And so why does our wave looks more frequent when you shorten the wavelength? Well, in actuality, it changes the speed. Light travels differently going through different materials. travel slower when you go from air to corn oil. So only the wavelength gets shorter, but so does the speed. Speed and wavelength go down together. So choice 1 is not our answer. It's frequency and period. They're inverses of each other. If you keep your frequency constant, you keep your period constant as well. Frequency always stays constant. Speed, wavelength, and direction, they change. The angle direction changes. So as your N value of your material goes up, because you're definitely going from 1.0 to definitely more than 1.0 here. As your N value goes up, your wavelength, your speed, and your angle of refraction all go down together. But frequency is constant. That always stays constant. All right, number 24. Still talking about light in corn oil. The speed of light ray in corn oil is blank. So I need our reference table because I don't remember off the top of my head what the N value for corn oil is. But we needed to solve for speed. So let's pull it out. Okay, so now I pulled it up. Corn oil's N value. This is on your reference table. You got to poke around for it. It's 1.47. So that's the N value for corn oil. And we are using this equation, N equals C over V. N for corn oil is 1.47. This is ratio for vacuum to corn oil. 1.47 equals C, that's the speed of light in a vacuum. 3 times 10 to the 8th meters per second over V. And we're solving for what V is. So 3 times 10 to the 8th divided by 1.47 is our answer. I'm screwing up here. 2.04 times 10 to the 8th meters per second. And that's choice 2. Number 1, the spreading out of a wave after passing through an opening in a barrier is an example of, so I'm going to draw it right here. We get wave fronts approaching this. They bend through the opening. And then they sort of curve around like this, and that's how waves are able to spread out. And that's called diffraction. That's what diffraction looks like to illustrate what this wave phenomena is. Number 26, a microwave with a frequency of 5 times 10 to the 10 hertz has a period of blank. So frequency and period are inverses of each other. So T equals 1 over F. And you just have to take the inverse of our given frequency. And you should get our answer. And that is choice 1. 2 times 10 to the negative 11 seconds. It's really short. Number 27, after 2 light waves have interfered in a vacuum, the 2 waves will be blank. So when light interferes, anything with interference, either destructive or constructive, they both result in a change in amplitude. Okay. Now, if you're looking at your answer key, why isn't it choice 3? Because in actuality, it's not choice 3, choice 2, or choice 1, it's choice 4. Now, the thing is, what confused me at first, and now reading it carefully, it's kind of like, oh, that's dumb. So this happens during. During interference, there's a change in amplitude. Before / after, the 2 waves go off their merry way. So it's unaffected. So let me draw this on a side spiel for you guys. Okay. So this is what happens before. These 2 waves are going to approach each other. This is what happens during interference. And this is what happens afterwards. So after they pass through each other, they just continue on their merry way as if nothing happened. Hence why our answer choice or answer to this question is unchanged. Because really what this question is asking about is what happens after the fact, which makes me feel dumb. You know, because my first instinct was to go for answer choice 3, and I bet it was 2 for most of you. But if you read this question carefully, it's choice 4, and hence why this particular Regents was basically half 50% of reading tests before you even do any math. So you gotta read these questions carefully. If you're like me, you're gonna rush, and so take it slow. A glass rod is rubbed with silk. During this process, a positive charge is given to the glass rod by doing what? Alright, so you need some chemistry background knowledge for this. Positives and negative charges, how do we even attain these? And it's through the process of adding or removing electrons. We are not changing our number of protons at all, because if you change your protons, the number of protons, you change the element, and we can't do that. They're stuck in the nucleus, they can't move barely, they can barely move. But electrons are very mobile. They can move between objects, they can move throughout objects, they're very versatile and mobile. Okay, and they are pretty much the ones that determine charge. So we gotta remember that electrons are negatively charged. So if you add, it becomes more negative. If you remove electrons from an object, they become more positive. So how did the glass rod become positive? It was removing electrons. It had electrons removed from it, and that's how it became positive. So just to highlight, these are some things to look for. Alright, number 29. A photon with an energy of that many joules has a frequency of blank. So energy in photons and their frequency. So the dual nature of light. E equals hf. H is Planck's constant at the front of the reference table. So energy in the photon, 1.33 times 10 to the negative 21 joules equals Planck's constant, 6.63 times 10 to the negative 34 joules seconds times F. And F is equal to 2.01 times 10 to the 12 hertz. And that's choice 2. The speed of a car is increased uniformly from 11 meters per second to 19 meters per second. The average speed of the car during this interval is blank. So here we have our two speeds, and if we're looking for an average speed, we're just going to add these two together and divide by 2. We get 30 divided by 2 equals 15 meters per second, and that's choice 2. Okay. Number 31, the energy equivalent of the rest mass of an electron. So energy and mass together equals mc squared. We're looking for E, or energy, and the mass is your mass of the electron, and that you need to look on the front of the reference table for the mass of the electron, which I also need to look up because I don't remember it off the top of my head. And don't forget it's in kilograms. Okay, you get 9.11 times 10 to the negative 31 kilograms, and that's really small. That's your mass of the electron, times c squared. C is the speed of light in a vacuum, and don't forget that's squared. So don't forget that c is squared. And you'll get something close to 8.199 times 10 to the negative 14 joules, and that rounds to choice 2 as our answer. Alright, a spring has an unstretched length of 0.4 meters. The spring is stretched to a length of 0.6 meters when a 10 Newton weight is hung motionless from one end. The spring constant of the spring is blank. Alright, so here we have a spring with a 10 Newton weight attached to it. That 10 Newton weight is the same as the spring, as the force in the spring. So 10 Newtons is our Fs. We're looking for a spring constant K, and X is the amount of compression or elongation. So it's being stretched from 0.4 to 0.6. The amount it's being stretched is the difference between them, and that's 0.2 meters. So Fs equals Kx. 10 newtons equals K times 0.2 meters. K is 10 divided by 0.2, or 10 times 5, and that'll get you 50 N/m, choice 4 for number 32. Number 33, here we have a circuit. Ooh, circuits. 3 lamps and a switch and a power source. So here usually our current starts here, conventional current. It reaches this junction, it splits up between these two paths, but hey, we have an open switch. So when the switch is open, it can still go through lamp 1, but now it's stuck here. It can't go anywhere. It can't reach lamp 2 or lamp 3. It's only going to go through lamp 1. It's going to stop at that junction. Oh, I don't know what I'm doing. Okay, there you go. And alright, it's going to flow through here. Nope, not at all. Just through lamp 1. So this branch gets canceled out, and so does that one. So it's just choice 1. Lamp 1 only. So when they say open switch, that means it's just as shown in the diagram. No pathway, no closed loop. And finally, we reach our last 2 questions of just part A. This is the longest part of the exam, in my opinion, when I always make these videos. But anyway, let's get started. Number 34 and 35. 34 is talking about electric fields, and electric fields always flow between 2 things. They always flow from positive to negative, out from the positive and into negative. So from the positive direction, they should point outwards, and in the negative source, they point in. And looking at our 2 parallel plate fields, choice 2 is not correct, and it's choice 1. If you're like me, I always like to think of it this way. Positives radiate happiness, negatives suck in happiness. So that's how I remember the direction of the field. Positives radiate out, negatives suck in. There you go. Number 35, which points on the wave diagram below are 90 degrees out of phase with each other? So out of phase means they're not corresponding, whereas in phase means corresponding points. So out of phase means non-corresponding. So we can't use points that are pretty much corresponding to each other, like B and C. So B and C are corresponding, and so is A and E. They're also corresponding points. So let me just write some reasons in there. 90 degrees out of phase. So that means we have to think of some things. So 360 degrees is also the same as 0 degrees, which is in phase. That's a full wave. .180 degrees is out of phase, and that's half a wave. Which is what C and D are. That's half a wave. That's 180 degrees out. And so that leaves us with D and E, because 90 degrees means quarter of a wave away. Quarter of a wave out of phase with each other. If we think about a full wave, it's a full crest and a trough, up and down. C and D are half of that away from each other. They're opposites from each other, crest and a trough. D and E are just half of a trough, half a crest, so on and so forth. That's a quarter of a wave. That's 90 degrees out of phase, and that's why choice 4 is our answer for number 35, and that is the end of just part A. We still have 50 more questions to go, but it ain't over yet. Okay. Just stay tuned for part B1, B2, and C.